In this lecture, we will discuss the application of cycloconverters in electric drives. This comes under Module 3. First of all, let's see what is a cycloconverter. It is a converter which is capable of varying the frequency. That means a cycloconverter is a frequency changer that converts AC power at one frequency to AC power at another frequency by AC to AC conversion. That simply it is a AC to AC converter which can vary the frequency of the output voltage. This is the basic block diagram of a cycloconverter. Basically, there will be two converters, for positive converter and a negative converter. In every cycloconverter there will be a P converter and an N converter. Both will be feeding the same load, AC load. This AC in our course electric drives, we will be discussing the application of cycloconverters in electric drives. That means this AC load will be an AC motor. It may be a single phase induction motor or a three phase induction motor or a synchronous motor, and there will be a control unit which will be controlling both the converters. This is the basic block diagram. Next, we will discuss the different types of cycloconverters. There are different methods to classify the cycloconverters based on the output frequency. They can be classified as step-up cycloconverters and step-down cycloconverters. Step-up cycloconverters means the frequency will be boosted. That means the output frequency will be greater than the input frequency. And for step-down cycloconverters, the output frequency will be less than the input frequency. This is another method to classify the cycloconverters based on the number of phases. Single phase to single phase cycloconverter, three phase to single phase, and three phase to three phase. Now we will discuss all these classifications. First of all, we will discuss a single phase to single phase cycloconverter. It can be implemented in two different methods. First is midpoint type and the other is bridge type. Both of them will be having the same output voltage. The only difference is that they are different circuit configurations. So we will discuss single phase to single phase, midpoint type and bridge type. Now let's see how a midpoint type converter works. Here there are two converters in this cycloconverter. A positive converter, that is the switches P1 and P2, and a negative converter, that is the switches N1 and N2. That means in this converter there are two different converters cascaded. They will be feeding the load. This is the AC load to be fed by this cycloconverter. The same midpoint type converter can be used as a step-up converter or a step-down converter according to the switching pattern. Next, let's see how this midpoint type converter can be operated as a step-up cycloconverter. That means the frequency of the output voltage will be greater than that of the input voltage. Here P1 and P2 are the positive converter group and N1 and N2 will form the negative converter. So in this waveform, this is the source voltage waveform. The source voltage waveform, the frequency is Fs. So the time period Ts is equal to 1 by Fs. And this is the inverted waveform of the source voltage. So in order to multiply or in order to increase the frequency, first of all the switch P1 is turned on during the positive half cycle. That means during the positive half cycle of the source voltage, this terminal will be positive and this will be negative. Then we will first of all switch on P1 alone. So the current will flow in this direction through load. So the current is positive, and also the voltage, output voltage is also V0 is also positive, and this is the waveform during this time period. That means when P1 is turned on, the output voltage will be this, up to this. Now we will turn off P1 and we will turn on N2. That means one of the switches in the positive group is first turned on, then after a while we will turn on one of the switches in the negative group, that is N2. When N2 is turned on, since the input voltage is positive, the current will flow in this direction, that means negative direction. Current will be flowing in the negative direction, and also the output voltage is negative. So the output voltage will be like this during the turn on period of N2. Again, after a short time period, we will turn on P1. Then the output voltage will be like this. Like that, we will get this alternating voltage. After the positive half cycle, we have the negative half cycle. During the negative half cycle, first of all we will turn on P2. That means this switch P2 is turned on. That means during negative half cycle, the terminal B will be positive, so the current will obviously flow in this direction like this. So current is flowing in the positive direction through the load, and also the load voltage, output voltage is also positive. So this is the output voltage, and after a while we will turn on N1. During the turn on period of N1, the current will be flowing in this direction, that is from this terminal through load through N1 and back to source. So the current, direction of current has reversed. So current is reversed, also voltage is also reversed. So this is the output waveform. Like that, P2 and N1 are alternately turned on and off. We will get this waveform. That means during the positive and negative half cycle of the source voltage, we have 1, 2, 3, 4, 5 and 6 pulses or 6 cycles of the output waveform. That means if the supply frequency is Fs, the output voltage frequency will be 6 times the source voltage frequency, 6 times Fs. That is the output frequency. Or F0 is equal to 6 times Fs. Now let's see how the same converter can be operated as a step-down cycloconverter. Step-down cycloconverter means the output frequency will be less than the input frequency. This is done like this. During the positive half cycle of the supply voltage, the switch P1 is turned on. That means the current will flow in this direction. So current and voltage are positive. So the output voltage will be like this. During the negative half cycle of the supply voltage, we have to invert this voltage so that the output will be positive. So in order to invert that, it will be operating like a rectifier. The converter has to operate like a rectifier. So we have to turn on P2. So we will turn on P2. So the current will flow in this direction. So the output voltage and output current will be positive. From the current will be flowing in this direction itself. So we will alternately turn on and off P1, P2, P1, P2 according to our requirement. So until we turn on P1 and P2 continuously, we will get only positive pulses or positive half cycles. Then after a while, when we have to get the inverted voltage, we will operate only N2 and N1. Let's see what happens when N2 and N1 are operated. When during the positive half cycle, of the input voltage, when N2 is turned on, when N2 is turned on during positive half cycle, the current will flow in the negative direction through N2 like this. So current is negative and also voltage is negative, output voltage is negative. Again N1 is turned on during the negative half cycle. So when N1 is turned on during negative half cycle, the current will be flowing in this direction, that is through the load in the negative direction. So the voltage is also, output voltage is also negative. So that like that, when N2 and N1 are continuously turned on and off, we will get only negative half cycles. So when we take the average voltage or average output voltage, this dotted line is obtained. This is the dotted this is the average value of the output voltage. So this is the positive half cycle and this is the negative half cycle of the output waveform. So we can see in this case the supply frequency is reduced, the output frequency is less than the supply frequency. Now let's see what happens when the firing angle is also controlled in the case of a cycloconverter. Figure B shows the same waveform that we have discussed earlier. Here the firing angle was not controlled. In figure C, the firing angle of the positive converter and negative converter, that is alpha P and alpha N, both are equal to 60 degree. So when the firing angle is increased, that means the output voltage waveform will have a reduced magnitude. So the dotted line shows the output voltage, the average output voltage. So the average value of output voltage is somewhat lesser than the previous case. That means figure B, less than the figure B. Now in third case, that means figure D shows a case when the firing angle is not uniformly controlled. That means for the first pulse firing angle is 60 degree, and for the second pulse firing angle is 0 degree, and for third one also firing angle is 0 degree, and for the fourth one the firing angle is again 60 degree. So the average value of output voltage is somewhat like a stepped waveform. Dotted line shows a stepped waveform. This is according to the requirement of the user. That means if our drive demands this type of waveform, you can switch the cycloconverter like this. So the basic thing is the cycloconverter can be used either as a frequency controller alone, or it can be used as a frequency controller as well as a voltage controller. Now let's see how this converter operates in discontinuous conduction. The operation is almost similar to that of a fully controlled rectifier. You can see these waveforms. These are familiar to us. This is the waveform of a fully controlled rectifier during the positive pulses, and the negative pulses are just the inverted waveforms. So this dotted line shows the fundamental component of the output voltage. We have already seen this square waveform, average output voltage as a square pulse, but the fundamental component of that waveform is shown as the dotted line here. So the sine wave will be like this, the output voltage will be like this, and we can see the output voltage frequency is equal to 1/4 times the supply frequency. That means the supply input voltage completes 1, 2, 3 and 4 pulses when the output voltage completes 1 cycle. This is how the frequency is reduced. So it is a step down converter. This we have already discussed, and we can see here the firing angle is also controlled. And this the figure C shows the current waveform. So So here we can see this is discontinuous conduction. So the current waveform touches the x-axis, and for a small time period the current remains 0. Again it increases like that. The same operation as a fully controlled rectifier which operates in discontinuous conduction. This is shown in order to understand how the drive will operate, or the current of the drive will be when it is used for driving an AC motor. This is how the cycloconverter operates in continuous conduction. The waveform, voltage waveform is similar to that of a fully controlled rectifier which operates in continuous conduction. And also the figure C shows the input current waveform, and figure D shows the output current waveform. Current is continuous. Now let's see how a single phase to single phase bridge type cycloconverter works. The bridge type cycloconverter will have a positive converter and a negative converter. Since it is a single phase converter, the positive converter is having 4 switches and negative converter is also having 4 switches. Both are fed from the same supply voltage Vs, and both are feeding the same AC motor, single phase AC motor, that is a load. So whenever the output should be positive, then only P converter is operated. Whenever we need a negative voltage, then N converter is operated. Like that, the frequency of the output voltage is controlled, but the remaining things are the same as that of a midpoint converter. That means the output waveforms, the discontinuous and continuous conduction operations, everything will be the same as that of a midpoint type converter. The only difference is in the circuit configuration and control of the circuit. Remaining things are the same, so it is not discussed again. Now let's see the operation of a 3-phase to single phase cycloconverter. A 3-phase to single phase cycloconverter is also having 2 different configurations. One is half wave configuration, which has only 6 switches. The positive converter is having 3 switches, negative converter is having 3 switches. Both are feeding the same load and both are fed from the same supply, 3-phase supply. The bridge type converter is having 6 plus 6, 12 switches. Positive converter has 6 switches, negative converter has 6 switches. Both are feeding the same load and both are fed from the same 3-phase power supply. Now let's discuss the operation of a 3-phase to single phase bridge type cycloconverter in detail. Here the basic principle of operation is the firing angle alpha of the 2 converters, positive converter as well as negative converter, is first decreased starting from an initial value of 90 degree. That is, initially the firing angle is set at 90 degree, then it is decreased to 0 degree, then again it is increased to a final value of 90 degree. Let's see how it. Now let's see the output waveforms. The first switch will be triggered at alpha is equal to 90 degree here. So the output voltage will be like this. This is the output voltage. Then the second switch will be triggered at a firing angle less than 90 degree. Then the next switch will be triggered at again the firing angle alpha is reduced. Then again alpha is reduced. Again alpha is reduced, like that. The firing angle here, the firing angle alpha is equal to 0 degree. Then again from the next pulse onwards the firing angle is increased from 0. Here again increased, here, and here it becomes alpha is equal to 90 degree. Like that, we will continuously increase and decrease the firing angle in order to get the wave pattern like this. So when we take the average value of this output voltage, we will get this sine wave like this, and the sine wave shows the fundamental component of the output voltage. Actual output voltage is this pulsating one. It will contain harmonics. We know we have to admit that the cycloconverter output is having more amount of harmonics than that of the other type of converters, but if we can sacrifice on if we are okay with the harmonic content, then we can better go for cycloconverter, which is easy to control. And this shows the current waveform, which is somewhat lagging behind the input voltage. This is the 3-phase to 3-phase cycloconverter, which is formed by cascading 3-phase to single phase cycloconverters. The operation of 3-phase to single phase cycloconverter is already explained, so there is nothing to discuss in the case of operation. But here we can see this 3-phase to 3-phase converter is feeding a 3-phase motor. This motor may be a 3-phase induction motor or a 3-phase synchronous motor. Both are having a property that its speed can be controlled by controlling its frequency. That is, synchronous speed ns is equal to 120 f by p. So speed is proportional to frequency. So a cycloconverter is the best converter in order to control the speed of an AC motor. But the only problem is that the output waveform of a cycloconverter has a much amount of harmonic content. Thank you.